Okay, so let us start. Last time we talked about order of the linear multi-step method, and then we see that how to compute an order of the method, and also we see that how we can use the order of the linear multi-step methods to derive a linear multi-step method, right? So that is what we did, and we derive a Euler method, right? So I believe we derive an explicit Euler method by using the procedure, right? And then I ask you to derive other methods as well, right? So today we will see one more example, and then we will continue to the next part, right? So let's say right, so let us derive the linear two-step method of maximum order. Right, so let us say we want to derive that. So first we will fill out the information we have. Right, so you know that it is a two-step method, so you know you have to have k is equal to 2. And also clearly you know that alpha 2 is 1. That is obvious, right? So k is 2 because it is a two-step method, and alpha 2 will be always 1. You can set that. And then they say it is explicit. So because of that, beta 2 will be also 0. And so this is one additional information we have. This is explicit method, right? So this is because of that. Right? So this part implies this, and two-step method. So that gives us is 2 information. Right? Because it is a two-step method, you know k is 2 and alpha 2 is 1. Because it is explicit, you know beta 2 is 0. So now what you have is, you know, you will start C naught is equal to 0. So alpha naught plus alpha 1 plus alpha 2 is equal to 0. Right? So this gives me alpha naught plus alpha 1 is equal to minus 1. Right? So I have equation number 1. Then I will go to C1 is equal to 0. That gives me, right, then I have alpha 1 plus 2 alpha 2 is equal to minus beta naught plus beta 1 plus beta 2 is 0, right? So plus, so that is 0, right? So that is what you have. So from this you will get alpha 1 minus beta naught minus beta 1 is equal to negative 2. This is your second equation. Right, so still the equations are not enough to compute all of them, because you have to find alpha naught, alpha 1, beta naught, beta 1. So you know there are 4 unknowns. So at least you should have 4 equations. Right, so you have 1, 2. So you need to get 2 more equations. So you will go to C2 is equal to 0. And so you know the formula for C2, so you can make the substitution. Right, so sorry, I'm going to alpha 1. Right, so C2 is summation of j squared times j squared over 2 alpha j minus summation of j beta j. Right, so then half of alpha 1 plus 2 squared over 2 alpha 2, right, minus 0 times beta 1, sorry, 0 times beta naught plus 1 times beta 1 plus 2 times beta 2, but beta 2 is 0, so you can have this. Right, so this gives you what? So 1 over 2 alpha 1 minus beta 1 is equal to 2 minus 2. So that is your third equation. Right, half alpha 1 minus beta 1 is equal to minus 2. Next one, or you can say it's okay. Next one, you say C3 is equal to 0. So that's 1 over 3 factorial 6. 8 over 6 alpha 2 minus 1 over 2 factorial j over 2 factorial beta. So that is minus 1 over 2 beta 1. So this gives you 1 upon 6 alpha 1 minus half beta 1 is equal to minus 8 over 6. This is equation number 4. Right, so you simplify this. So now you have 4 equations, 4 unknowns, right? So you can compute the value. So by solving equation 3 and 4, you will be able to get alpha 1 and beta 1, right? So you combine 3 and 4 together will give you, if you subtract one from the other, minus the 2 beta 1 is equal to minus 4 plus 8. Right, so 2 minus 1 is beta 1 is equal to 4. So alpha 1 is equal to 4. And then equation 1 gives you alpha naught is equal to minus 1 minus alpha, so that is minus 5. And then we take equation 2 gives you beta naught, it's alpha 1 minus 5 minus beta 1 minus 4 minus 9. Alpha 1 4 minus beta 1 4 0. So minus beta naught is minus 2, so beta 2 naught is 2. Okay, so you have 4 equations and then you have 4 unknowns. So you solve them and you get the values. And so after getting the values, you should be able to write down the equation or the method. Then, so this is what we have, right? Alpha 2 y2 yn plus 2 plus alpha 1 yn plus 1 plus alpha naught y naught is equal to h times beta naught f n plus beta 1 f n plus 1 plus beta 2 f n plus 2. This is the method, right? So if you have a two-step method, this is how it will look like. Alpha 2 yn plus 2 plus alpha 1 yn plus 1 plus alpha naught yn is equal to h times beta naught fn plus beta 1 fn plus 1 plus beta 2 fn plus 2. Now you substitute the values. The alpha 2 is this, so yn plus 2, alpha 1 is 4, so plus 4 yn plus 1, alpha naught is minus 5 yn is equal to h times beta naught is 2 fn plus beta 1 is 4 fn plus 1 and then beta 2 is 0. So this is the linear multi-step method which we are looking for, right? Now we want to find the order and error constant, right? So if you want to find the order and error constant, then you can continue and get what is order and what is error constant, right? So part 2, I will say find the order and error constant. Right, so you find it order and the error constant. Okay, so if you want to find the order and error constant, so you know you already go up to C3. Right, C3 is equal to 0, you already do. So you will try to find C4. Right, so you can find C4. That is if you write the formula for C4, that is j is equal to 0 to 2 alpha j to the power 4 over 4 factorial, right? Sorry, j to the power 4 over 4 factorial into alpha j minus j to the power 3 over 3 factorial into beta j. This is the formula for C4, right? So you have a formula for CQ, so you can substitute it. And so when you put j is equal to 0, you get 0, j is equal to 1, so 1 over 24 alpha 1 plus 2 to the power 4 is 416 over 24 alpha 2 minus of j0 is 0, j1 1 over 6 beta 1. And so this is what you have for C4. And you already know alpha 1, alpha 2 and beta 1. So you can substitute. Right, so 1 over 24 times alpha 1 is 4 plus 16 over 24 times alpha 2 is 1 minus 1 over 6 times beta 1 is 4. Right, so you can simplify this. So 20 over 24 minus 16 over 24. So it's 1 upon 6. And so you can check this number and see whether this is correct or not. Right. Okay, so this is obviously non-zero. So clearly order is 3. Error constant. One upon 6. So this is how you derive a linear multi-step method of a given order, or a given linear k-step method of maximum order, right? And then you can find the error constant and the order of the method as well. So this is another usage of. Now what we are going to do is we are going to define something called consistency of the method. So first, already what we defined is order of the method. Now we are going to see the consistency of the method. So we are going to define the concept called consistency of the method. Right. So we consider okay, so let us consider a k-step method in the standard form. Okay, so let us define the standard linear multi-step method. Right, so this is how we define the linear multi-step method in general. So let us say we define it like this. Right. So in this linear multi-step method, first what we are going to define is, we are going to define what do we mean by consistent. Right. So to do that, right, so first let us define what do we mean by local residual error at yn plus xn plus k. Right. So we define it as T of n plus k. That is basically okay. So we define the local truncation error by if left hand side minus right hand side, both sides evaluated at xn plus j. Right, so instead of using the approximated value yn plus j, we will use the real value y at xn plus j, right? So you know that this yn plus j is the approximated value, but y at xn plus j is the real value, and fn plus j is the approximated value of the function. F at xn plus j comma y xn plus j is the real value of the function. Right? So we will define this as the local residual error. So we already gave a notation for that earlier. Okay, so you can notice that. Right, so we use this. Right, so we defined earlier this one. So this is an alternative notation of way we define the locus truncation error. Right. So now we are going to define what do we mean by consistency. Right. If the limit of the local truncation local residual error divided by age is equal to 0 as age goes to 0. All right, so this is limit. And limit age goes to 0 tn plus k. So you define tn plus k as here, that is the local truncation error, goes to 0 as age goes to infinity, then we say that the method is consistent. So we shall check, we shall define the consistency as this: local truncation error divided by age will goes to 0 as age goes to infinity. But you know that checking this limit is very difficult, because for every method you have to find this, right? And then you have to find that value and then divide by age, and then you have to take age goes to infinity, age goes to 0, and you have to check the limit. That is a difficult work. So we will try to find some alternative conditions which are easy to check to verify the consistency. Right? So in order to do that, right? So in order to see an alternative condition to check the consistency of the method, let us define two more things. They are polynomials We name that as first characteristic polynomial and second characteristic polynomial. The first characteristic polynomial right? So the first and second characteristic polynomials as right. See, rho is the first characteristic polynomial, that is alpha j times z to the power j. Sigma is the second characteristic polynomial, that is beta j times z to the power j. So let us see an example of this first. So first, to derive or define a characteristic polynomial, you should have a linear multi-step method. So let me define a multi-step method like this. Right, so let us say there is a linear multi-step method like this. Right, so yn plus 3 minus yn plus 2 plus 2yn plus 1 minus 5yn is equal to h over 8 2fn minus 3fn plus 1 minus 2fn plus 2 plus 5fn plus 3. So you can define the first and characteristic polynomials as follows. Right, so rho of z is summation of alpha j z to the power j. Right, so alpha naught, so that is minus 5 plus alpha 1 z plus 2z minus z squared plus z to the power 3. And so this is your first characteristic polynomial. Now second characteristic polynomial is beta j times this, so 2 upon 8 minus 3 upon 8z minus minus 2 upon 8 z squared plus 5 upon 8 z cubed. Right, so this is how you define first characteristic polynomial and second characteristic polynomial. Okay, so this is how. This is first characteristic polynomial and second characteristic polynomial. So by defining the first and second characteristic polynomial, right? So we will see an alternative condition for the consistency of the method. I will write this as a exercise. Right, so the condition is a linear multi-step method is consistent if and only if the first characteristic polynomial evaluated at 1 is 0, right, and the second characteristic polynomial evaluated at 1 is same as the first characteristic polynomial derivative of that evaluated at 1. So this is what we do. So you know that consistency if and only if, right, limit h goes to 0, tn plus k over h is equal to 0. Right, so you know that. But that is same as limit h goes to 0, L of yxn h over h equal to 0. Right, so you already know that, or we just write down, or we notice that this is what we have, right? So L of y comma xn is this. But you have a formula for L, right? When we talk about order, 1 upon h times for L of yxn at 8, you have a formula. Right? If you remember, we define a formula in terms of y, c0, c1, c2, c3, and so on. Right? So c1 8 y prime of xn plus c2 h squared y2 prime of xn plus so on. Right? And that is 0. Right? So this limit must be 0 because limit of ln over h is 0. So if we simplify this, when h goes to 0, right? So if we simplify this, that is c naught over h times yxn plus c1 y prime xn plus c2 h y2 prime xn plus so on is equal to 0. Right? Because when you divide by h, c naught over h by xn, c1 h cancelled out y prime, c2 h squared over h is 8 y2 prime, and all of them will have h there. And so when you take limit h goes to 0, you know that everything after this will automatically be 0. So you don't need to worry about that part, that will automatically 0. But because the limit is 0, these two has to be 0. Right? So So if you want to have this limit to be 0, then what you should have is, you should have C naught is equal to 0 and you should have C1 is equal to 0, right? Because all the others are automatically 0. This, all of them are 0, but the whole thing should be 0. So this has to be 0. So if this has to be 0, you know this cannot be 0. So this will automatically be 0. This has to be 0. So automatically C1 should be 0. Right? So only the limit will be 0 if and only if both C0 and C1 are 0. But you can write the formula for C0 and C1. Right? So you remember C0 is summation of j is equal to 0 to k alpha j is equal to 0, and this is j is equal to 0 to k j times alpha j minus beta j is equal to 0. And because you know the formulas, so you can substitute them. Right. So this is same 0 to k alpha j is equal to 0, and this is j is equal to 0 to k beta j is equal to 0 to k j times alpha j. Right? But we already defined first and second characteristic polynomials. Right? So if you put z is equal to 1 on the first characteristic polynomial, you will get summation of alpha j is equal to 0. And if you put 1 on z is equal to 1 on the second characteristic polynomial, you will get summation of beta j. And if you take the derivative of the first characteristic polynomial, you will get j times alpha j z to the power j minus 1, and then you put j is equal to 0. So alpha is equal to 1. You get this. This is basically equivalent to rho of 1 is 0 and sigma of 1 is equal to rho prime at 1. Okay, so if you have a linear multi-step method, right, where the first characteristic polynomial evaluated at 1 is 0 and the second characteristic polynomial evaluated at 1 is equal to the derivative of the first characteristic polynomial evaluated at 1 is same, then we can say that the method is consistent. So instead of taking the whole limit and setting that equal to 0, right, you could have easily checked whether the first characteristic polynomial is 0 at 1 and the second characteristic polynomial at 1 is same as the derivative of the first characteristic polynomial at 1. And so that is how you can verify the consistency of the method. Right? So we will stop here, and in the next class we will see a relationship between this condition and the order of the method. Right? So that is what we are going to do next in the next class tomorrow. We will try to see a relationship between this condition, right, these two, and the order of the method, so that once you see that condition, then you can combine consistency with the order of the method. So you already know how to find the order of the method, so you can easily check the consistency by just finding the order of the method. Right? So that is what we will start. That is where we will start tomorrow, and after that we will talk about stability and convergence of a linear multi-step method. Right? So we will talk about all of that in next class.